My name is Theo Ra, and this is my lab video report for Lab 2 on projectile motion. This is what the video will cover, starting from introduction all the way to conclusion. The purpose of this experiment is to compare the motion of a projectile with a prediction by a computational model, with or without drag put into account. Here are the related concepts to this experiment. Newton's second law states that the net force is mass divided by acceleration. Therefore, force needed to speed up or down an object is proportional to its mass. Net force is when multiple forces are in effect to a single object. Its motion depends on the net, so the sum of them all. Here are the used formulas for this experiment. The velocity update formulas states that the final velocity equals initial velocity plus Fnet over mass acceleration times change in time. When net force is 0, the change in velocity is also 0. The position update formula states that final position equals average velocity times change in time. We will use these to calculate object's position and velocity in the computational model later. And then you can see the force of gravity formula, which states that gravity equals minus mass times gravitational constant, which is 9.8. Drag force formula, as you can see from the bottom, states the force of the drag acting on the object. Here you can see the experimental preview of the object. You can see that the x position is rising steadily, which is reasonable because there is no gravitational effect on it. And on the lower graph, you can see the y position going up and down due to the gravity. Overall, the result of this experiment matches the expectations that we would have according to physical concepts. Here is the image of the object and the components. The system of this experiment is a scrunched up paper ball weighing 4.5 grams, and the surroundings are all others. Procedures. 1. Record the video of throwing the paper ball up and it falling down, which is the projectile motion. 2. Analyze the video through Tracker. 3. Construct the computational model through GlowScript with or without drag force. 4. Upload results to Excel and compare graphs. Here are the initial conditions that I set using Tracker. On the initial position, x is 0.291 and y is 0.302 meters. And on the final position, time equals 5 seconds, x is 1.073 and y is negative 0.8996. And the drag constant I set to be 0.01. This is the image of my tracker analysis. You can see the mass points being plotted. Here are the initial conditions that I set for GlowScript. Mass, first of all, is 0.0045 grams. Well, 1 is grams, so 0.0045. And the position and velocity are same as the initial conditions that I used for Tracker. Delta T is 0.033. Gravitational constant is 9.8, and you can see that the drag factor is 0. At the bottom of the right image, I used velocity and position update formulas to model the object. Here is the image of my program run with my initial conditions. Secondly, here are the initial conditions for the GlowScript with drag put into account. Everything else is same, but you can see that B equals 0.01, and the F drag force is put into account in the second image. Here is the GlowScript program run with drag. Here are the results comparison. As you can see, the actual results and the prediction through the computational model is quite similar. For some reason, the prediction with drag put into account showed to be farther away from the actual result. What are the possible sources of error? Firstly, it could be human error that I made in mass point placements. They were maybe a bit off from the actual position. Secondly, movement of the camera when filming the video could have an effect. And thirdly, incorrect air drag variable might have messed up the results. Questions. First question. None of my models show terminal velocity. There was always a net force not equal to 0 working on it. If I wanted to model an experiment that show terminal velocity, we could imagine something similar with higher velocity so that the drag would be greater and make the net force 0. If the object was initially thrown straight up, it would reach a higher maximum height and longer time to hit the ground.